Good morning. I'm Bill Buynitzky with Cormetech, and I'm suspicious that the last name is the reason we skipped the introductions this morning. I'm going to just talk a little bit about combustion turbines and SCRs, and just go ahead and talk a little bit about the general experience that's out there, the basics of the SCR reaction and how the catalyst works. The trends we're seeing in terms of turbines and performance requirements, and then we'll just sort of summarize everything up here at the end. So SCR is a very established technology, originally developed in the 1970s, primarily used in Japan, moved into Europe in the 1980s, moved into the US in the 1990s. It's used in a number of applications. You can see a fair percentage of what Cormetech's installed base is based on combustion turbines. And in the US, that's primarily natural gas fired. We do have a few other applications, and there is some co-firing, but primarily when you're talking about combustion turbines in this country, you're talking natural gas. And so I'm going to start off basically going through everything from a natural gas basis, and then I'll hit on some of the differences as we change fuels later on. The industry has managed the changing requirements. When the technology first came in, the requirements were not as strict as what we have now. There's been a continual improvement, trying to, you get these occasional feelers of, how low can you go in terms of NOx and slip. And the industry has just looked at those changes and adapted the technologies to them, designed, whether it's the change of the turbines themselves or regulatory. There have been a series of changes that have been going on through this process. So the typical SCR reactions are the ones that are shown there. The top one is the one that almost everyone will talk about. It's normally talked about as NO plus ammonia goes to NOx, goes to nitrogen and water. People generally leave off the oxygen component of it, because the oxygen's in abundant. When people are talking about the reactions, they're talking about the things they're concerned about, which is the NOx they want to get rid of and the ammonia they have to inject. There are two other reactions in a gas turbine that can be there. The second one is when instead of having pure NO, you have NO2. So the NO plus NO2 and the ammonia, that's actually a slightly faster reaction than the standard SCR reaction, so that's all well and good. The last one is a pure NO2 reaction. So if you've got a high NO2 turbine, or CO catalyst can also raise the NO2 numbers, you can wind up with this slower reaction as you wind up in a NO deficient regime. This reaction is a lot slower than the other two. And the other thing to look at there is it actually requires more ammonia per NOx. And all that's important. There's a short quiz later on in the presentation where we'll go over this again. So, but those are the three main reactions for a natural gas application. We will have some others down the line. So then you get into how do you prove the performance of the SCR? And this is important for a couple of reasons. It's not just necessarily the regulatory testing. These are also often the contractual ways that the industry is set up to prove that the SCR is performing at its specified level. It's almost always done at full load, because that's generally been the condition that determines the amount of catalyst that is required. It's also generally considered to be the maximum emission rate, which is why it normally will wind up being the case for regulatory agencies to want it to be tested there. And then it's the EPA methods are generally used. They're generally pretty accurate. They're generally the best we have, and they're easy to agree upon, particularly in this country. They're also often used outside of this country as the reference methods, because other people recognize them as being an efficient and an accurate way of measuring the emissions. So the thing to think about on those methods, and I'll touch on this again later, is some of the methods, particularly for measuring ammonia at CTM 027, it's a 1 hour integrated wet chemistry sample, and the importance of that will come up as we move down the line here. And then, of course, the the facility is required to report. And generally they have continuous emission monitoring. We've had different rolling times. This is one of the places where regs have changed in different states, view things differently. 1 hour is becoming more common. 24-hour and 30-day rolling averages are all fairly common that we see. The thing to think about that is when you've got a fairly long averaging period, you get large percentages of time at full load. The startup shutdown periods become less important. And so you've got the predominant operating mode and reporting mode becomes steady state operation. Historically, gas turbines don't run very well at heavily reduced loads, so you're typically looking at loads on the turbine of 75 to 100%. So you're talking as close to full load as the grid demands, but that's the operating mode that the turbines have been in. In terms of reporting, they've often had exclusionary periods for the startup and shutdowns because systems aren't steady and it's hard to get good numbers. And then the facilities obviously have to certify their instrumentation. Normally those are, again, EPA regs, the performance specifications appropriate for the monitor. And what we're seeing in the trend here is that we're looking at reduced averaging times. Certainly less than 15 minutes. I've seen requests where they're talking about regulating on a 6-minute average. And they're increasing their focus on the high NO2 and reducing or scaling back these startup allowances. And these are important because as you reduce that averaging time, the transition of the turbine as it goes from low load to high load or vice versa, that becomes a much more relevant part for controlling and reporting your emissions. It's no longer going to be these long periods of steady state with a short couple of minutes of ramping time. It's going to be, it could be the entire 6-minute period could be a ramping mode. And that's important because the SCR has absorption-desorption cycles for the ammonia and NOx. So as you're trying to manage these changing conditions, that's going to be a little bit more challenging. The turbines themselves are changing. The industry wants units that basically work like a light switch. You turn it on, you're at full load, and they can keep their grid running. They're all happy. The other main difference we're seeing is we're seeing some turbines where they're talking about parking them basically at idle, so spinning reserve. The turbine's running, it's hot, but it's not producing any output. And that way, as the grid demand comes up, they can just ramp that turbine up because they don't have that soak period for getting everything up to temperature and equilibrized. Some of that is being driven by other energy sources that are available. Some of it's due to the fact that we're using more gas turbines, trying to reduce the amount of coal. That's an economical decision that they're making, but they want these turbines. The one turbine doesn't have the range that a coal power plant generally did, and they're generally a little bit, on the Hersig part, they're slower, on the GT part, they're faster. So the industry is trying to balance all of these factors to make sure that they've got a reliable grid, but still meet all their other requirements. So the short-term challenges we're seeing on the SCRs are these shorter averaging times and the removal or shortening of startup exclusions. The turbines themselves, particularly at low loads, can have higher emissions. So you may have a turbine that running at full load, it's putting out 20 or 15 ppm of NOx. As you go down to try and run this turbine at 20% load, that NOx may go up to 35 or 50 ppm. So this changing dynamic of the industry of how they're trying to run can put them in regimes where we may not be looking at full load being the controlling case. The shorter averaging periods and the more ramping we have may put us in a situation where the changes in the turbine operation and its subsequent impact on the SCR is actually what's going to regulate the volume of catalyst or the catalytic performance that's required to control the unit within these regulatory regimes. So we are ready for the quiz, right? Hopefully it hasn't been too long since I went over all this. So does anyone remember which one has the highest ammonia demand? Yeah, it's the all O2 reaction. And the other part is which one is the slowest? It's the same one. So I wanted to do that as a reminder, because as we start to think about transients, think about the turbine that's starting at low load and then coming up. And like I said, at low load we can have high NOx and high percentages of NO2. So this is an example of a transient performance we've worked on. In this case, it's a hot start. Ramp rates are a little bit more beneficial, and the SCR is in a little bit better place than doing this from a cold start. So right here you've got the inlet NOx, and it's starting off fairly high, around 35 ppm. And it's going to drop down to this steady state around 15 as the turbine comes up to load. So if you have to start to inject ammonia in this early phase in order to meet your requirements, in this case we didn't have to do that. On a cold start you probably do. So you've got this combination of high NO2, high NOx, transitioning down. So you'd wind up with this large amount of ammonia you'd have to come in with early, trying to get the SCR up to performance, get the ammonia absorbed on the catalyst and start to reduce. And then as all of a sudden that turbine load's coming up, its NOx is dropping, probably the NO2 ratio is dropping off. So controlling that transitionary period is going to be very complicated. Typically, from an instrumentation point of view, plants have only done post-SCR, and they've used a feedback control mechanism. As we move forward, there's been some thought that we may need to put another NOx analyzer upstream of the SCR to try and get a feed-forward system so that as you can tell as the NOx is going up, you start reacting sooner. I'm not entirely convinced that's going to be that beneficial, and my reasoning on that is the flue gas flow rate through the SCR area runs about 5 to 7 meters a second, which means it leaves the turbine and goes out the stack in about 10 seconds. Now, if you're familiar with the NOx analyzers, their time to hit a stable answer is about 30 seconds, and that's from gas hitting the back of the analyzer. If you've got one where you're trying to speciate and they're switching between measuring NOx and just NO, then they're slower than that. And then you've also got how long does it take to get the sample out of this ductwork to the analyzer. So you're dealing with a system where the analyzer is probably 2 or 3 minutes behind what's going through your system. When you think about trying to control for a 6-minute averaging period, if your analyzer is only telling you the last 4 minutes of that 6-minute period, it makes it a lot harder to be able to manage that control process. So the analyzers are going to be part of the issue. And then the testing methodologies on top of that, we talked about, and I mentioned CTM 027 for ammonia, and you start to look at how do you contractually prove that your ammonia at 20 minutes is at, in this case it's less than 4 ppm. Well, CTM 027 is a 1-hour integrated sample. So how do you know where you are 20 minutes in versus 25 minutes in? The industry needs to figure out on a way we can all agree on how to do this testing, because until you can agree on how it's going to be tested and measured, you're going to have trouble getting people being willing to guarantee it. If you can't measure it, it's really hard to prove what you're doing. So then the other fuels, I just talked about oil just a bit. In this country, generally we're talking about number 2 diesel. It's low sulfur. There is an SO2 oxidation reaction for SCR catalyst. It's fairly straightforward. SO2 plus oxygen gives you SO3. The SO3 is bad. It tends to promote the ammonium sulfates more than the SO2. You see that some with oil, and that these cases controlling that SO2 oxidation may be a desire. Normally that hasn't been a significant factor. We're seeing some inquiries about biodiesel. That's better on the sulfur, but brings a different set of deactivation agents for the SCR. Natural gas is nice because it's basically free of deactivation agents. So the catalyst is long-lived. As you move into oil, be it distillate or bio-derived, you're introducing deactivation agents to the SCR. And so those have to be accounted for in the design. You see some kerosene it's in the same general ballpark as oil. And then we're seeing more and more inquiries about digesters and landfill gases. I think we all know that landfills release a lot of methane. It makes sense to generally use it for something beneficial. Certainly from a greenhouse gas perspective, it makes sense to do something with it. They're problematic in that the stuff we put in landfills, primarily we use a lot of things with siloxanes, and so siloxanes are our issues with these. The siloxanes are a very strong deactivation agent for the SCR. Basically, you put a glass coating across the surface of the SCR in short order. So the siloxanes have to be removed to quite low levels for the SCR to have a low life. We're talking single-digit part per billion range in the fuel. Has been the general trend. Those are hard to do and hard to maintain. So I'm just going to quick summarize. The turbines themselves are creating new issues for performance, and the methods in which those turbines are being requested to operate are creating new challenges for the SCR. The reporting may cause challenges. One of the things we never know is whether or not these are going to be hard and fast rules, or whether we have an agency exploring what is the current state of the art, what is the best available, what's the maximum achievable. So we get feelers on that. It's hard to say whether or not some of these are feelers, or whether there's a strong desire actually to push the industry in these ways. So the regulations can be pushing these. Again, sometimes we have agencies calling us up, asking us for what state of the art, can something new be achieved? But these new regulations are going to create new challenges for the SCRs, for gas turbines. But I think the main message here should be that the industry has a history of responding to these challenges. We've done it for, SCRs now are in the 40-year-old range. We'll continue to meet these challenges. It's just a question of timing on all of these and whether or not we can do them in the time frame that makes everybody happy. All right. Thank you again.